The graph of cosine has a maximum at x equals 0, where the graph is flat. What this suggests is that the derivative of cosine at x equals 0 is 0, because the derivative is equal to the slope there, which is 0. Writing this out in terms of the definition involving the limit, we see that 0 should be equal to the limit as h goes to 0 of cosine of 0 plus h minus cosine of 0 all over h. Because cosine of 0 is just 1, this limit becomes the limit of cosine of h minus 1 all over h. In summary then, by investigating the graph, we've determined the value of a limit involving cosine. It's also possible to determine the value of a limit involving sine by investigating its graph at x equals 0 as well. Although it's not entirely immediate, the slope of this sine curve is actually equal to 1 at x equals 0. A fact which could be verified by using the squeeze theorem together with some trig identities, as the textbook does. We won't concentrate too much on the justification in this video. Instead, let's just look at what this means for the slope to be equal to 1. Well, because the slope is the value of the derivative at x equals 0, we find that 1 is equal to the limit of sine of 0 plus h minus sine of 0 all over h. Sine of 0 is just 0, so we obtain the limit of sine of h over h. In total then, we can conclude that the limit of sine of h over h as h goes to 0 is 1. These two trigonometric limits involving cosine and sine are useful for at least two reasons. First, they give us more algebraic manipulations that could be useful when computing limits. For example, suppose we'd like to compute the limit of sine of 7x over 2x as x goes to 0. One of our favorite techniques for evaluating limits is using an algebraic manipulation that can make the limit more obvious, but in this case, it's not entirely clear what type of algebraic manipulation could be useful, especially among the techniques we frequently used before. Thankfully, we now know a new limit, namely the limit of sine of h over h, which, from the way it's written, as a fraction involving sine, appears that it might be useful in this situation. The only difference is that h is now replaced by 7x, or 2x, depending on how you look at things, so we'll have to make a change of variables. It turns out that the change of variables h equals 7x should do the trick. Notice that once we define h in this way, the variable h then goes to 0 as x goes to 0. And so we can think of the limit of sine of h over h as being equal to the limit of sine of 7x over 7x as x goes to 0. Now, the trick is to ensure that this type of fraction of sine of 7x over 7x appears in the limit that we're considering in the problem. For that limit though, even though we have a term that looks like sine of 7x in the numerator, there's no term that looks like 7x by itself. So, what we can do is introduce the 7x term ourselves by dividing the numerator and the denominator by 7x. Once we've done so, we realize that our limit is equivalent to the limit of sine of 7x over 7x all over 2x over 7x. The denominator is just 2 over 7, which is a constant. Because we're dividing by this constant, it's the same as multiplying by its reciprocal, so we could write that we're multiplying by 7 over 2 instead. And because this is just a constant, we can pull it out in front of the limit. And what we're left with is 7 over 2 times the limit of sine of 7x over 7x. Because the limit appearing here is just equal to 1 from our considerations that we did earlier, the answer just becomes 7 over 2. Another reason these new trig limits are useful is because they allow us to compute the derivatives of trig functions. For example, let's try to compute the derivative of sine at the point x. By definition, this derivative is equal to the limit as h goes to 0 of sine of x plus h minus sine of x all over h. Using the sign of a sum rule, we can rewrite the term sine of x plus h as sine of x times cosine h plus cosine x times sine h. Then, we see that sine of x is a factor common to two terms in the numerator, so we'll factor it out. Next, we'll write the fraction as a sum of two fractions, each of which we're taking a limit of. Because the limit is being taken in the variable h, any term that doesn't involve this variable can be factored out. So we'll pull out a factor of sine x in the first term and a factor of cosine of x in the second. What we realize then is that the remaining limits are exactly those that we discussed at the beginning of this video. The first, involving cosine, is equal to 0, and the second, involving sine, is equal to 1. After taking these limits then, what we're left with is sine of x times 0 plus cosine of x times 1, which is just equal to cosine of x. Taking a look at what we proved then, we realize that the derivative of sine x at x is equal to cosine of x. In other words, d dx applied to sine x is equal to cosine of x. It's also possible to perform a similar computation to get the derivative of cosine, which turns out to be minus sine of x. From a geometric standpoint, these formulas make sense. Because sine and cosine are both periodic functions, so too should be their slope functions, that is, their derivatives. In addition, the peaks and valleys of the cosine graph, for example, are points where the graph has zero slope, and these occur at integer multiples of pi, which means that its slope function should achieve the value 0 at these points, which is true of the sine function. The derivatives of the rest of the trig functions are listed in the table below. One of the things to note is that those functions which have a co in front of them always have a minus sign appearing in their derivative. In addition, their derivatives are the counterparts of those functions without the co in front of them. For example, while the derivative of secant x is secant x tan x, the derivative of cosecant x is minus cosecant x cotangent x. One of the ways in which these derivatives of the other trig functions can be obtained is by using quotient rule. For example, tangent is equal to sine over cosine, which is a quotient. And so the quotient rule should give us a formula for its derivative. It's perhaps an interesting and useful exercise to verify that the quotient rule actually gives that this derivative is equal to secant squared x as a final answer.